Hey everybody, Dr. A here, and in this video we are going to be exploring an example of heave under Artesian pressure in a cut, okay? So let's go ahead and look at the given information. Here we're being asked to compute the maximum cut depth, which we're calling capital H, that can be made in the clay layer if there is a sand layer beneath it under Artesian pressure, okay? So if we take a look at this given diagram, what do we have here? Well, we have a ground surface here, okay? And we want to make some kind of cut in this ground surface to a depth H, but we don't know what that depth H is, okay? Now, the clay layer that we are dealing with is 25 feet deep, okay? And then beneath the clay layer, we have this 10-foot sand layer. Now, the clay layer, which is, this layer here, has a saturated unit weight, which is a type of total unit weight of 120 pounds per cubic foot. And then that 10-foot sand layer that we have here has a saturated unit weight of 115 pounds per cubic foot. Now, a piezometer was installed at the elevation of the interface of the clay layer and the sand layer. So this line right here is the interface between the clay layer, which is above, and the sand layer, which is below. The piezometer was installed, and water that was that's in the sand layer causing the pressure rose up the piezometer by 5 feet. Okay, so clearly this is not to scale. We can maybe make a note here, that this is NTS, not to scale. All right. So the question becomes, again, how deep can we cut into this clay layer so that you don't have blowout or heave at the bottom of the cut, right? That's what we become concerned about, is if you cut down too deep, you have this pressure buildup from the sand layer, and it'll blow out the cut. All right. So let's go ahead and figure out how we tackle this. Well, under solution, we're going to make a note of this. We're going to say the maximum cut height is the depth H at which the bottom of the cut will heave, okay? Now, what happens with heave? Well, heave or blowout or boiling, all of these terms refer to a lack of stability or a loss of stability, okay? So we're going to say heave occurs due to a loss of stability, okay? Which means that your effective stress goes to 0, all right? Now, the point that we have labeled for us is this point A. Point A is at the interface of the sand layer and the clay layer. So the loss of stability would be at that interface. So we're going to say at point A, all right? So when effective stress goes to 0, how do we set this problem up? Well, we have to remember that effective stress is equal to total stress minus pore pressure at a given level, or in this case at point A, okay? So now what we have to do is set up some expressions for total stress and pore pressure, and we need to combine them together and set that equal to 0 for the case of investigating heave, okay? So how do we do that? Well, total stress is just going to be equal to what? Well, we're cutting into the ground at a distance h. So you have to ask yourself, what is everything that's going to be above this point A when we make the cut? Well, it's going to be this material right here, all right? So what is the distance here? What is the distance of this material? Well, it's 25 feet minus h. And what is that material? Well, it's saturated clay. So here I'm going to say we have 25 feet minus h times gamma sat of the clay, okay? What about the pore pressure? What about the pore pressure at A? Well, point A is under Artesian pressure, right? And so that's measured by what's happening with this installed piezometer. So we said the water level rose up by 5 feet in a piezometer, okay? So the Artesian pressure, or the pore pressure that's happening at point A, is going to be the unit weight of water times 5 feet, the height that the water rose in that installed piezometer, okay? So if we piece this together, we can say sigma prime A, the effective stress, is going to be total stress, 25 feet minus H times gamma sat clay, which is the 120 PCF from the given information, total stress minus pore pressure. So minus 62.4 PCF, that's the unit weight of water, times 5 feet, okay? And so that is our expression for effective stress. Well, remember, for heave, when heave is going to occur, we said it earlier, heave occurs when sigma prime A equals 0. So what we need to do is set this expression equal to 0. All right, so I'm going to repackage this a little bit, and I'm going to say 25 feet minus H times 120 PCF minus 5 feet times 62.4 PCF equals 0. Now what I can do is do some rearranging and solve for H. So just showing a little bit of my algebra work, I'm going to have 25 feet minus H equals, if I gather some constants, that's going to be equal to 2.6 feet, and then do last bit of rearranging, H is equal to 22.4 feet. So what this means is this is the maximum cut depth just before heave occurs. Okay, so I would say, I would not cut directly to 22.4 feet. I would maybe cut to a depth a little bit shallower than that. You could build in a factor of safety somehow and, have a factor of safety take care of a safety margin. You could cut down maybe to 20 feet or 18 feet and have some safety in there, or the problem could be posed with an actual factor of safety that you could divide in there and cut at a shallower depth. But this will be the depth that just causes the loss of stability, okay? So hopefully you found this video helpful. If you did, please hit like and subscribe.